The following program is brought to you by Caltech.
Good evening. I'm Tom Sofer, the chairman of the Division of Physics, Math, and Astronomy. Before I introduce tonight's speaker, I want to remind you the next Watson lecture will be on February 15th. It will be Professor Liat Yariv, Professor of Economics, and she will speak about what parents want, evidence from child adoption. I hope you can be here. So it's my distinct pleasure tonight to introduce our speaker, Jim Eisenstein, who's the Frank J. Roshek Professor of Physics and Applied Physics. Jim received his PhD in physics from Berkeley and has been a professor of physics at Caltech since 1996. Before that, he was a distinguished member of the technical staff at AT&T Bell Labs. Jim is a leading member of the condensed matter physics community, and he's the co-director of Caltech's new Institute for Quantum Information and Matter. Among his many honors, Jim is a member of the National Academy of Sciences. In 2007, he shared the Oliver E. Buckley Prize of the American Physical Society, the APS's most prestigious award for work in condensed matter physics, for fundamental experiments and theoretical research on correlated many electron states in low-dimensional systems. Tonight, Jim will describe the amazing world of emergent phenomena in condensed matter physics in his talk, Electrons in Flatland. Jim.
Well, thank you very much, Tom. Almost everything that he said was true, in fact. This is the topic of my talk is probably going to seem somewhat obscure to many of you. So I tried to use images like this one that bring across the basic concepts in a simple way. I also thought that it would be a good idea to start the talk by telling you what the punchline is right away, so that in case you get bored and you want to leave, you'll know the answer anyway. And I'll do that. I'll do that with this picture, which is very important in Caltech's history. So this is the Rose Bowl. This is the Rose Bowl in 1961, where the Washington Huskies were fighting the Minnesota Gophers. And during the halftime celebration, as you can see, Caltech performed one of its most famous pranks of all time by managing to steal the instructions for the card display and show the word Caltech instead of, I don't know whether it was Washington or Minnesota at the time that was supposed to come up. So this was a wonderful thing. I mean, when you stop and think about how difficult it must have been to do this, it gives you some pause. Now, why do I say this is the punchline? The reason this is the punchline is because of what's said at the very bottom here, that the whole is greater than the sum of the parts. Each one of those people that's holding up one of those cards is just an ordinary person, has no real idea of the overall structure of what's going to appear. Holding up a card, it might be a dark card, might be a light card, but in the end of the day, if you add up all those people together, something comes out. The word that we use in physics nowadays is something emerges from the complexity of this large number of people together doing something. In this case, the word Caltech comes out. So that's the punchline. You can go to sleep now if you'd like. That's really what I've got to talk about. The whole is greater than the sum of the parts. Now, I also want to begin 100 years ago to give you some perspective for what's going on. And I'm going to tell you about two experiments which were done about a century ago. One by this fellow, who you will recognize, I assume, as being a prestigious member of Caltech's own administration and faculty. So this is Mr. Milliken, whom in 1913, before he was at Caltech, he was at the University of Chicago at the time, did a famous experiment, quite a famous experiment. It's called the Milliken oil drop experiment. Most undergraduates who take physics at one time or another at least try to do this experiment. I remember trying it actually when I was in high school. It's kind of hard, but it's a fun experiment. The point of the experiment is the following. There's a bunch of droplets of oil which are squirted out with an atomizer, and they fall through a hole. They get observed by Mr. Milliken looking through a microscope or through a little telescope to see those drops of oil. The drops of oil are charged. They're charged by virtue of, I think, a radioactive source in this case. The charges land on those, that occur on those droplets are what he wanted to measure. And by putting different voltages on these metal plates indicated by these red things, he could suspend the droplets and then write down in his lab notebook what the voltage was that was needed to suspend the droplets. And by so doing, he was able to determine that the electron, which was a particle that had been known about only for about 10 or 15 years at the time of this experiment, had a charge given by this particular number. Doesn't matter what the number is, but that's what he managed to do. Previous experiments had not been able to determine the charge on the electron, but Mr. Milliken managed to do it. He also did something there's another very important aspect to this experiment. He found that no matter what droplet he looked at, it always either had this charge, or twice this charge, or 3 times this charge, or 4 times, or you get the idea. Never 2.5 times this charge. So he concluded correctly that, in fact, in nature, all charges are multiples of this one number. Not fractions of it, but multiples of it. Okay, so that was a very important experiment, and it dealt with the property of one electron. Also, in the same time frame, about 100 years ago, this fellow came along, one of my favorite physicists. This is Kamerlingh Onnes, working at the University of Leiden in the Netherlands, and he did an amazing experiment. He managed to liquefy helium. Helium, of course, is a noble gas. It's the lightest of the noble gases. He liquefied it in 1908 at a temperature of 4.2 Kelvin. And by the way, this is a very typical picture of how physics works. There's an experimentalist sitting here. He's wearing a lab coat, and he's working very hard. And there's a theorist standing here. This theorist is Johannes van der Waals, famous theorist, and he's giving unsolicited advice to the experimentalist. This happens all the time. Now, in case you're not familiar with what 4.2 Kelvin means, you can think of it as 269 degrees below 0 centigrade. Or if you still don't think about centigrade, you can think of it as minus 452 degrees Fahrenheit. It's darn cold. It's very close to absolute 0. So this guy did an experiment, and it's important to think about the context of this experiment. He was doing something which I think most people thought was crazy at the time. He was working in an environment that no one thought anything would ever useful come out of it. What was he trying to study? Turns out he was trying to study, at the time, one of the applications of this liquefaction of helium was to study the properties of metals, how they conducted electricity. And people didn't understand how it worked in 1910. There were all kinds of theories out there. What he found, though, didn't agree with any of the theories. Which is another great lesson about experimental physics. Just go do the experiment. You're almost certainly going to find something that nobody thought of, in spite of van der Waals coming and giving all the advice. He found that mercury was very strange. He chose mercury, by the way, because you can make mercury very pure. So he chose mercury, and he found out that the resistance versus temperature went down and down until it got to 4.2 degrees Kelvin, the same place helium liquefies, and then, boom, the resistance went to 0. Or at least it became smaller than anything he could measure. And he was a very good experimentalist. Try as they might, below 4.2 Kelvin, they couldn't detect any resistance whatsoever. So this was a tremendous surprise. They had no idea what this was about. And this was, of course, the discovery of superconductivity, which I will have more to say about. This is an example not of the property of a single electron, but an emergent property of many electrons. So it comes back to this sort of paradigm that I'm trying to draw out. All right, there again is the essence of the talk. I've now written it in mathematical form. The whole is greater than the sum of the parts. What else is emergence? Let's talk about another example of emergence just to drive the point home. Let's take an example from biology. Everyone in this room is filled with these things, neurons. You can think of neurons sort of analogously to the single electron. It's an elementary object that we know a lot about. Maybe not everything, but we know a lot about neurons. They have these dendrites at one end, this big thing called the axon, and they can communicate with one another both chemically and electrically. So think of them as the object. Think of them as the one Caltech student holding the card in the audience at the football game. But then, Take 100 billion of those, more or less, depending on, how smart you are, and you get one of these. This is 100 billion neurons put together. And I would argue that nobody understands how the properties of this emerge from that. So this is a very extreme example, but I think it's a really good one. Let's go back to these electrons. Ordinary metals, and I mean metals that aren't superconductors, take copper, for example, you can think pretty accurately of the properties of copper in terms of the individual electrons which move around in it. You don't need to think about them collectively. It suffices to think about them individually. However, in mercury, if the temperature is low enough, that description fails because it becomes a superconductor, and we now know, 50, 60 years after Onnes's discovery, that something very collective occurs whereby the electrons in mercury at low temperatures choose to form pairs, something you would never have predicted had you not first made the experimental discovery of superconductivity. And it took 50 years to figure this out. Okay. Now, what's the context of today's talk? So I said at the beginning, this is electrons in flatland. So flatland is just what it sounds like. It's a flat surface on which somehow or the other I put some electrons. If you don't like that image, use this one. This is perfectly good. Think of the electrons as the balls on the billiard table. Unless you're a really poor billiard player, they will remain on the table while you play. That's not always true, as I'm sure some of you know. They can hit one another and scatter. They can hit the boundaries. They can even, if you're lucky, fall into the pockets and become localized. Well, how do I make these things? There's a variety of ways, and I'm only going to say something about the one that we use the most often in my own lab. It turns out that what we do is we take semiconductors, which are kind of material. They're not metals, and they're not insulators. They're kind of halfway in between. And we make a layered, sort of a sandwich structure of material A, material B, and then material A again. With material B, the thin one, think of it as a piece of ham in your sandwich, being quite thin. Very, very thin, maybe 100 angstroms or so in thickness. We do that, make it thin like that, so that the electrons, which we will now put into that thin slab, can't move in the direction perpendicular to the interface. They're confined. However, if we're good experimentalists, we make the surfaces, the interfaces between the material A and the material B, we make them as perfect as you can possibly imagine, every atom being lined up with its neighbor, so that when electrons move in the direction of the plane, they're free to do so, or as free as they can possibly be. How do we make this thing? Well, we start with a machine that's a complicated machine called a molecular beam epitaxy machine. Forget the word. Think about spray painting. Think about buying cans of spray paint at Osh that contain different atoms. A gallium spray can, an aluminum spray can, an arsenic spray can. They're hot cells that contain vapors of these atoms. And have the whole thing set up in an ultra-high vacuum chamber and have a substrate of the material on which you wish to grow this layered structure. And then open up these containers. First open the gallium and the arsenic containers to grow a new layer. And if this substrate is hot, those atoms will not simply fall on random spots. They may fall on random spots, but they will then migrate and want to find the right spot to sit. I mean, after all, the world made crystals for a reason, as opposed to amorphous materials. And then if you like to grow a different kind of material, you open up the green can and spray down a different kind of set of atoms. And in this way, I think you can imagine growing a layered structure, any kind of thing that you might want. That's how we produce this, in which we confine these electrons. Now let's talk about some experiments. Let's go back even further in time. 1879, Edwin Hall, a student of Rowland, US physicist, was interested in the electrical conductivity properties of thin films of metal. It's interesting that he didn't know electrons existed, but he knew that electrical currents did. It was still 20 years, or almost 20 years before electrons were actually discovered. He took some gold leaf which you know what gold leaf is, and he connected a battery to it and drove an electrical current through it. He then came along with a magnet, and he put a magnetic field on the gold leaf and looked at various voltages which appeared in response to the current. And in particular, he found something very surprising. He found that if he looked for a voltage in the direction transverse to the direction that the current was actually flowing, there would be such a voltage in proportion to how strong the magnetic field is. This is called the Hall effect, not surprisingly. He would have won the Nobel Prize if only Nobel Prizes had existed in 1879. It's an immensely important experiment done hundreds of times every day throughout the world for all kinds of reasons. Very, very useful experiment. Well, that's fine. So now let's jump forward, try to not make this an ancient history talk, and go exactly 100 years later, doing the same basic experiment, except not with gold leaf, but with one of these two-dimensional electron systems, or electrons in flatland systems in the semiconductor that I told you about. I'll introduce this guy. This is Klaus von Klitzing. He won the Nobel Prize in 1985 for the experiment I'm about to describe. So he just did exactly what Edwin Hall did, nothing different. What did he expect? Well, he thought that he would see a voltage, a sideways voltage, and it would go up in proportion to the magnetic field, just like Edwin Hall had seen. That's not what he saw, though. He found this. No one predicted this. No one had any idea what it was to begin with, but you sure couldn't miss it. He found a staircase. Not only did he find a staircase, but he's a very good physicist. He's also a metrologist, so he knows about measuring things accurately. He found that these plateaus, the steps, were really flat, flatter than he could tell how flat they were. In fact, we believe they are perfectly flat. So that's very strange. It couldn't be more different than what Hall had seen. And he not only saw that they were flat, but he found that they appeared in an interesting sequence. If he called this one number 1, for voltage 1, it doesn't matter what the units are, the next one was at 1/2, and then 1/3, and then 1/4, and then 1/5, exactly. He could predict them all based on the first one. And he got out his textbook and looked up the fundamental constants that are always in the back of the book, and he found that, you know what? The ratio of the voltage to the current that I'm putting through, that's a resistance, turns out to be given by this formula. Now, this formula won't mean much to many of you, but let me try to describe it a little bit. This thing called E, well, that's what Milliken found. That's the charge on the electron. H, the very famous constant, this is Planck's constant. This is the constant that determines how the quantum world works. And if you take H and divide by the square of the charge on an electron, you will get von Klitzing's plateaus, provided you divide by an integer, 1, 2, 3, 4. This was a tremendous discovery. It was well worth the Nobel Prize, 1985, as I said. Well, let me try to explain this to you. And I won't give you a good explanation. It's not so simple, but I can give you some idea. So you all know about how atoms work. Electrons fly around the nucleus. You also know that if you know only one thing about quantum mechanics, you know that it means that electrons in atoms have only certain energy levels that they can be in. And so I've kind of made a cartoon of that with the different radii for those orbits. They can only be certain sizes. And what is the result of that? Well, the most obvious result is spectral lines. The energy, the light that's emitted by an atom or absorbed by an atom can only be done at certain frequencies. That discreteness is the same thing as the discreteness of these orbits. Okay, now we're not talking about atoms, though. We're talking about electrons moving in a magnetic field. Remember, the big magnet is applied. So what do electrons do in a magnetic field? Most of us know they go around in circles. There's no nucleus anymore. They're just going around in circles. And if you think about it, what is quantum mechanics going to say? It's going to say the same thing it said with the atoms. You can only have certain size orbits. There can only be certain orbits. And those discrete orbits, really, the analogy to the spectrum that I showed you for the atom, are these plateaus in the Hall resistance. I can assign each one of those to one of those orbits. Okay, and I can see somebody in the audience already pointing to the thing that I'm not telling you, so I'll tell you now. Wait a minute. There's something else in there. Now, Klaus didn't have this data. Klaus had not quite so good data. And so that one that I'm pointing to and got the number 3/4 on, he didn't see that one. We see it all the time now. This is data taken down in the basement here. It's not even particularly good data by today's standards. But the point is the following. This was 1, this was 1/2, this was 1/3. This can't be 1 over an integer. It's 1 over 4/3. So this was a new discovery. And we now know that it's not uncommon. If you get better and better samples, meaning cleaner surfaces, better ability for the electrons to move, and you go to lower temperatures than even Mr. Kamerlingh-Onnes would have ever dreamt were possible, and you put on atrociously high magnetic fields, you get to discover plateaus all over the place. In fact, what you find is that Klaus's formula for the ratio of the voltage to the current still got the same numerator, but the denominator is not an integer anymore. It's now a fraction. It's a fraction, P over Q. And there's lots of these things, and they're very wonderful, and they were discovered somewhat later than the integer quantum Hall effect, and they're going to be something that I want to talk about today. In some sense, you can think of Mr. von Klitzing's discovery as the property of single electrons, again. This discovery of these fractional states, you cannot do that. Remember the orbits I told you about? Well, there weren't any other orbits that I didn't, that I tried to sneak by you that would give rise to these fractional states. I used them all to get the integers. So where the heck are these guys coming from? They're coming from something else. And the something else is an emergent property of the entire electron system. This is a cartoon that we cooked up a long time ago. I don't mean to explain what this thing is. It's an interesting picture. We could have a nice discussion about it. The basic idea is the following. The electrons in the sample, they pay attention to the magnetic field, for sure, to go around in circles, but they also pay attention to the other electrons, because the other electrons are repelling them, and everybody's repelling everybody else. And it's very important in order to minimize the energy that all the electrons do just the right kind of repelling of one another. They do a dance. They do a dance like this. Here, from Mr. Matisse, we see a dance. If you just took one person out of the dance, it'd just be another naked person standing there. But if you bring them together and they do something collectively, you see this dance. These electrons are doing a dance. Each one of the fractions, it turns out, is a different dance. Okay, so let's imagine that we could do an experiment where we could dive into this electron gas and while it's in one of these fractional states and swim around without disturbing anything and see stuff. What would we see? It turns out you wouldn't see much. You certainly don't see any electrons. They're all spread out quantum mechanically. You have no idea where they are. The electron density just appears to be uniform. And if you're at really low temperatures, like nearly absolute zero, you'll see basically nothing. It'll be a very boring exercise in scuba diving. However, if the temperature gets turned up a little bit, you'll see some other things. Some objects will appear to your view. Little discrete things, particles moving in the fluid. Two kinds, red ones and green ones for tonight's talk. What are these particles? Are they just electrons? Well, there's two kinds, so they're not just electrons, only one kind of an electron. What are they? Well, it turns out they're charged particles, all right, but they don't have the charge on an electron. They have 1/3 the charge on an electron if the fraction that I divided by was 1/3. If it was 1/5, they would be 1/5 of an electron. These things have been experimentally observed. So this is a bit of a shock, right? Should be. What would this guy do? he'd flip on his head. He said, you can't have that. I proved to you everything's just multiples of the charge on an electron. What's going on? These are new. These are new kinds of particles that exist in this peculiar emergent state of electrons in Flatland. They don't exist by themselves. I couldn't reach in and grab one, put it out on the table, and start doing experiments on it. It only exists because the whole electron system is there. It's an emergent property of the whole. It doesn't exist by itself. So we say these things have emerged from the complexity of the many electron system. These are the guys that discovered that. They all got the Nobel Prize too in 1998. Dan and Horst were the experimentalists who made the discovery of the fraction, and Bob Laughlin was the fellow that explained the theory of why they exist, explained what all those things are in that complicated picture that I'm showing you over there, with the staircase running up with all the different steps of different widths and heights and so on. So okay, now let's imagine doing some experiments on these funny objects. So let's start in the classical world. Let's imagine you get out your eggs in the morning and you take two absolutely identical eggs and you put them on the tabletop, and then you come along and you exchange them. You do that exchange, and if the eggs were really identical, and your wife had turned her back while you made the exchange, she turns back, she couldn't tell anything had happened if they were really identical. Okay? In the quantum world, it's not quite that simple. If you take two objects, well, in order to explain what I mean by not being so simple, I have to take a small digression. In the quantum world, the description of objects is more complicated than it is in the classical world. And we often speak in terms of something called the wave function. Don't worry about what it is. It's an abstract mathematical quantity that contains all of the information that we can possibly have about that system. So think of it as some math thing that you learned about once a long time ago, a function. You can also think about it, and this is maybe a better way to think about it, as a vector, a thing that points, an arrow, points to the North Star, let's say. In quantum mechanics, it's not how long the vector is that counts. It's where it points. It can even get reversed in direction. That's still the same. But if it points off in some other crazy direction, then it's different. Okay, and I realize I'm not explaining anything to you. I'm just using words. But just go along with me for a while. So let's go back and ask about this exchange of the eggs. Only now they're quantum eggs. They're identical, and we exchange them. Two possible things can happen. This thing called the wave function can either not change its sign, nothing happen to it at all, just remain identical, or it can get multiplied by -1. And I just told you that multiplying by -1 didn't really change the state anyway, so this isn't so terribly important. Okay? No change of state. In the three-dimensional world, the one we all live in, we have a vanity. We believe that the world is divided into particles that either do the one thing with their wave function when you exchange them, one kind of eggs, or the other kind of eggs. Electrons happen to get the minus sign. Protons do too, so do neutrons. But photons, particles of light, mesons, a high-energy particle, these guys don't change sign. So there's these two kinds of particles in the universe. That's all there are. This is a vanity of three dimensions. We call these two kinds of particles fermions and bosons, after Mr. Fermi and Mr. Bose. Let's now ask the same question with my objects in Flatland. Well, I can interchange them too. Ask what happens. Well, it turns out not the same thing. You don't get the plus or minus 1. Most of the time, and I'll explain what I mean by most in a minute, you get a funny number. It's still a number. It's a complex number, but it's still a number. But it's not plus or minus 1. So already you know something's weird. Something in this two-dimensional world is really different. Not only are the charges fractional, but something we call the statistics of the particles are fractional too. We don't call them fermions or bosons. We're so inventive with words, we call them anyons. This is no joke. All right. Now let's do a little more complicated experiment. These are all thought experiments. We don't actually do these things. Let's imagine we had some objects, a classical world again, arranged on the corners of an equilateral triangle, red, white, and blue, colors of some significance to us. And we do let's do two sets of experiments. Well, first on the left-hand balls, then on the right-hand balls. I interchange those two guys over on the left. Then I interchange the two guys on the bottom. And now let me do the same experiment on the other triangle, but I'll do the things in a reverse order. I'll do the ones on the bottom first, and then the ones on the left. Same operations, different order, different final result. It depends on the order of events in the classical world for distinguishable eggs. Okay, I just said that. If the eggs had been identical, clearly, you can't tell any difference in the final state. All right. What about in the quantum world? For electrons, doesn't matter what order you do them in. You do two interchanges, you'll get a minus and a minus, it's a plus one. Nothing happens. Bosons, doesn't matter. Get a plus one, doesn't matter. Anyons, anyone? Turns out it doesn't matter there either most of the time. And we're right at the front line of research now. I'm telling you something that we don't really even know is true. There's theoretical evidence, there appear to be some kinds of anyons which are even weirder than the other ones, where it matters which order you do the interchanges, in spite of the fact that they're identical. This is nuts, right? They have a fancy name. They're called non-abelian. Okay, let's not worry about the name. And the theorists, God bless them, told us right where to look. They said, look there. I love this place, because I discovered this one myself a long time ago. We didn't know anything about non-abelian anyons at the time. But this one's a special one. It's got a plateau and everything. It's a very strange one. It's fun to work with. They said that's where you're going to find them. And there's a project being paid for by Microsoft, believe it or not, devoted to looking for these things, trying to find them. I'll tell you why. Why would Microsoft be interested? Oh, I have to tell you something first. How do you do these things? What do you actually do? I haven't told you any experiments. You have to go into the lab. You have to get really cold. So you get this machine. It goes to 1/100th of a degree above absolute zero. Okay, pretty cold. Not super cold, but pretty cold. We have a new machine that you can't see here. It's over here that now goes to 1/1000th of a degree above absolute zero. Very, very cold. Cold is good. And you need a big magnet. Remember, all these experiments are done with the magnet. So you have to get a big one, about 500,000 times the field of the Earth down in the lab. Pretty big magnet. Not super gigantic, but within a factor of 3 of the biggest magnet, steady state magnet in the world. Okay, what else do you need? You need really smart people. And I have lots of them that come and work in my lab, either as students or postdocs, what have you, undergraduates come and work in the lab. They're the ones that make possible these crazy experiments. Okay, now let's go back to the ideas. So this is what I've told you. This talk went very quickly. That's interesting. It's got 80 transparencies, and I thought, I've never given a talk with more than 35 transparencies in my life. This is not going to work, but apparently it has. Okay, great. But anyway, these ideas that I'm telling you about are kind of nutty. And even if they're interesting and even if they're true, probably you think they're pretty useless. And you're not right. You're wrong. And I'm going to tell you why you're wrong. Let's first, are they? Okay. Let's first talk about Flatland. Is that really a place we can have? Is that something of any use? You've all got them in your pockets. Every microprocessor that you have has 1 billion of them in it. They're not exactly the same, but they're very close. There's a transistor known as a MOSFET, of which there are billions inside every CPU, that basically has a 2-dimensional electron system. It's a little higher density than the ones we use, but it's the same basic idea. So there's nothing strange about it. They've been around for a long time. They are the main element of all modern electronics. Okay? You don't carry around a magnet, by the way, I don't think. But you've got lots of two-dimensional electron gases. What about this plateau business? That any good? You might have thought that sounds pretty stupid. Not stupid. Those plateaus are really flat, part per billion. Better than, actually, that's the limit that we've been able to tell. They're better than that. What good could that be? Well, it turns out the whole world depends on them now for the standard of resistance. If you go to NIST, National Institute of Standards and Technology, used to be called the National Bureau of Standards, you will find this experiment going on all the time. It is the experiment that determines the value of the ohm that we use for all electrical measurements. So far from useless, this has had an enormous impact on science and technology. What about this? Now I have to say, I'm not so sure. I can't give you an existing example of non-abelian anions. I don't even know if they exist. But let me try to tell you why they might be useful. There they are. And I just told you that if I interchange two of them, by the way, there could be more than three. I just show three because it's a small number and I can draw a picture of it easily. There could be 50,000 of them arranged in some way. I interchange a couple of them, I'm telling you, get a new quantum state. Not the same one. Quantum states contain information. All the information about a system. So if you have multiple states, you might imagine that you could hide information in this system. You might walk into the talk late and see the three balls up there and have no idea how many times I interchanged them before you got here. The whole world history of those objects will determine what state they are in. And furthermore, if one of you comes in and decides to bang on the computer and knock one of them around, because life's not perfect, right? There's always bad things happening, interference, all kinds of things that you don't want to have happen. Is that going to change the state? Nope. Not making an interchange. The only way you can change the state is to actually make the interchange. It's hard to make the interchange. Little disturbances don't do it. So this is not only a place to store information, it's a place you might be able to actually process information. And let me tell you how that might be. So here's a picture, same thing. This is my colleague Alexei Kitaev, right here at Caltech, who had a very brilliant idea about how you might use this crazy idea to actually process information. What did he say? Well, and I'm going to dumb it down to a level that I can sort of understand. Let's say I had 5 of them, and they're in some state. I don't know what it is. They're in some state. And I want to do a computation. And I write a code which will interchange them in some particular way, like this. The set of interchanges is the program. The initial state is it's the initial state. The final state, if you like, is the answer to the computation. This is thought to be a way to perform quantum computation. What is quantum computation? Well, you all know what computation is. Computation is what we do all the time, again, with those little widgets in your pocket. Nobody does quantum computation yet. Quantum computation is a generalization on classical computation whereby you use the complexity of the quantum world. You can use it to great advantage in principle if we can really figure out how to harness it. This is not the only way by any means. In fact, this is the craziest way, in all seriousness, that people are discussing for possibility of doing quantum computation. The beauty of this way, if it ever works, is what I told you a moment ago, that the information is protected. It's hard to disrupt it. Little disturbances don't have an effect. Whereas in all other schemes that I know about of quantum computation, little disturbances are deadly. So that's the potential advantage. We're not there yet, not at all. Okay, so is that ever going to happen? Probably not in my lifetime. If John Preskill's in the audience, he'd probably throw something at me. But I don't think it's going to happen for a long time. But I'm not worried, because I think there's a probability it'll happen anyway, sometime maybe later. And let's go back to give it an illustration. And this is, to me, an extremely important point. This guy, Camerlingianus, was sitting around in 1910 and 1912, whenever it was, doing crazy experiments that were completely curiosity-driven. People would go into the lab, I'm quite certain, and say, what are you doing this for? This will never be useful. He discovered superconductivity. What good is that? Well, maybe you don't know. It's got some applications. Did you know that it revolutionized medicine? How many of you have had an MRI? I bet you a bunch of you have. MRIs work because superconductivity works. It's not the only physical principle by any means, but believe me, you couldn't make a magnet in which you could slide a body if you didn't have superconducting wires to make that magnet out of. So this is something, a good example to me of how long the timeline, how long the time horizon for crazy research really can be. In this case, it was at least 70 years before people had really functional, workable MRI machines for medical diagnostics. Okay, well, that's the point, an important point. And I think that with the case of quantum computation, we're in a somewhat similar situation. I would love to be the one who discovers whether these non-abelian particles exist. And even if they never make the quantum computer, it'll still be a crazy discovery and it'll be really exciting. But maybe in 70 years, they'll make the computer. Who knows? I wanted to finish up with one more vignette about Caltech. And I showed these pictures, which are Richard Feynman's last blackboards, taken obviously right after he died, showing the things that he was working on and thinking about. And you know, there's a lot of stuff up there, some very interesting statements. What I cannot create, I do not understand. Well, that's pretty profound. Know how to solve every problem that has ever been solved. That's a challenge, right? But those are the kinds of things he thought about. And then he had a list of, like a to-do list. Like I say, today I got to do this, tomorrow I got to do that. He had a list of things I got to learn. What are those things? There they are up there. Look at the third one. He wanted to learn about the quantum Hall effect. Unfortunately, he ran out of time. I'm sure he would have made a contribution to the field. Okay, and I'm going to finish with this picture. If you don't know anything about Flatland, go read this book. This was written in 1884 by Edwin Abbott. It's about what life would be like if we all lived in a two-dimensional world. But if you look really carefully at the picture up here, there's 10-dimensional land up there. My string theory colleagues are up there. And then there's 9-dimensional land. There's all different dimensions. But the book is about 2 dimensions. I think you'll find it enjoyable. All right, thanks for listening.